Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutiwa Sos Ugobela Wemets. And without any further ado, let's look at this question that we have here. Okay, so we have question 6 still on chemical equilibrium. It says carbon in solid state reacts with sulfur in gaseous state according to the following balanced equation. So we can see the balanced equation, and then our enthalpy change is greater than 0, indicating that this is an endothermic reaction. Now the system reaches equilibrium at temperature T in a sealed 2dm cube container. The Kc value is 9.4 at temperature T. 6.1 is saying state Le-Chatela's principle. Right. So to state Le-Chatela's principle, we know that it states Le-Chatela's principle states that when an equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. That's how you're supposed to define it for 2 marks. Now, at equilibrium, 1 mole of carbon disulfide, CS2, is present in the container. Calculate the concentration of sulfur gas present at equilibrium. Now we can see that we are given the Kc value, and then we are required to calculate the concentration at equilibrium. Now we can calculate that using the formula Kc is equals to the concentration of the product over the concentration of the reactant, right? And then note that we have a coefficient of 2, which must become an exponent. Now we don't include the carbon here because carbon, as we can see, it's in solid state, and we say the concentration of solids and liquids remain constant throughout the reaction. So they do not make it to the Kc expression. We do not substitute them into the Kc expression. Now, okay, to calculate here, for the carbon disulfide, we are given 1 mole. And then we are also told that this container has a volume of 2dm cube. It's simple to calculate the concentration for the carbon disulfide, because we only need to say concentration is equals to the number of moles over the volume. Now the number of moles, it's 1, and then the volume is 2. So this will give us 0.5 mole per dm cube. Right. So just like that, we have the concentration for the carbon disulfide. But then remember, we are actually looking for the concentration of sulfur. Now, for sulfur, we are not given the number of moles. That means we cannot calculate using this formula here. And then again, we cannot use ratios because we are at equilibrium. Remember, ratios can only be used on the change block. We do not apply ratios at equilibrium. Right, so that means we can only find the concentration using the Kc formula here. If we can substitute our Kc value, that's 9.4, and then substitute the value that we just calculated for our carbon disulfide, and then now we'll be left with finding the concentration for the sulfur gas. So all we need to do here is just cross multiply here, and then we'll have 0.5 divided by 9.4. Remember, we have sulfur square. So to find the concentration of sulfur, we just need to square both sides. And then concentration of sulfur, if you punch all that into your calculator, you get 0.23. So mole per dm cube. Note, we are calculating the concentration. So it has the SI unit. So 0.23 mole per dm cube becomes our concentration for the sulfur gas. So all that for 4 marks. Right. Then let's proceed. It says the volume of the container is now doubled. Note that every time they mention volume, I always told you that you need to immediately relate it to pressure, right? So if they're saying that they doubled the volume, what does it mean in terms of your pressure? It means that the pressure was decreased. So an increase in volume, doubling the volume means increasing the volume. So an increase in volume means a decrease in pressure. Now 6.3 says, how will the amount of sulfur gas change as this new equilibrium is established? Choose from increases, decreases, or remains the same. Then, okay, You know the strategy. I'm not going to answer that question as yet, but what I'm going to do is start by answering 6.4, where I explain the observation. Then 6.4 says explain the answer to question 6.3 in terms of Le Chatelain's principle. So I'm going to say, this is what I know. Observation is that doubling the volume actually does what? Decreases the pressure. So that's point number one. I'm going to get a mark for that. Just simply knowing the relationship between volume and pressure, that it's inversely proportional. Then number two, we know that now a decrease in pressure according to Le Chatelain's principle always favors the reaction that will produce more number of gas moles. So we'll say a reaction that will produce more number of gas moles be favored. Which means now we have to go back here and try to find which reaction actually produces more number of gas moles. So we're not going to consider the coefficient for carbon because it's a solid. Pressure is only applicable for gaseous molecules, right? So we have 2 and then we have 1 here. So the reaction that will be favored, of course, is the reverse reaction. So we'll say the reverse reaction is favored. Now, if the reverse reaction is favored, we know that thus concentration of sulfur gas will do what? Will increase. And then that means, what is our answer for 6.3? It should have been increases. And then now we also have the explanation. Doubling the volume decreases the pressure. A reaction that will produce more number of gas moles will be favored, which means the reverse reaction is favored in this case. And then thus the concentration of the sulfur gas will increase. Okay, so now we have a 6.5. It says if the concentration of the carbon disulfide changes by X mole per dm cube, write down an expression for the equilibrium constant Kc in terms of X. So let's draw our R.I.C.E diagram. All right, so now this is our R.I.C.E diagram, and if you can just check carefully, you will notice that it's different from the one I've been drawing on the previous videos. This one is actually based on the concentration and not the number of moles. Hence, you don't see that final row there, which says C is equals to N over V. Why this one though? It's because when I read here, they gave me my change in terms of the mole per dm cube, which is the concentration. So note that you can have your R.I.C.E diagram in terms of the number of moles, or you can have your R.I.C.E diagram in terms of the concentration, right? So now it's a matter of just having to read your statement and find which one will be best, right? So by the note here, if I have this one, there is no need for me to come and then have this final block here whereby I will have to divide everything by volume, because remember, everything that I will be putting in here will be the concentrations, right? But then again, the concentrations that I'll be substituting into my Kc expressions are the concentrations at equilibrium. It's always these ones here, the concentration at equilibrium. So now let's begin. We have our ratios here. If we can indicate that this block will be taking the 2s, and then this one will be taking the CS2, right? Now the ratios are the coefficients, so we drop down the coefficients 2 and 1, right? What was the concentrations here on the previous equilibrium? But then again, you have to note something based on that. So they did something here. They said the volume of the container is now doubled, right? So that means it has to affect those initial concentrations. Now, the concentration that I had at the previous equilibrium, remember, we had the concentration for CS2, and then we calculated it to be 0.5. It was 0.5 mole per dm cube. If you can just run it back to this question in 6.2. We had this one. But then remember now, what did they do to the volume? They doubled the volume. Now, what is the relationship between volume and concentration? We know that they're inversely proportional. But then this is what you need to notice. Double the volume means half the concentration, if that is the relationship. So if I double the volume, that means I have to halve the concentration. So initially the concentration would be 0.5. But then we also need to consider the fact that they did something to the volume, which affected my pressure, which then will affect the concentration. So if I have this 0.5 here, I need to then remember that I will have to divide that by 2, because the concentration now will have to be half. So this is 0.25 mole per dm cube. But again, it's not only the concentration of this that I found. I also found the concentration of sulfur, which was the one I was calculating in 6.2. Then it's 0.23. But again, let's consider what was done to the volume. The volume was doubled. So that means what must happen to the concentration? It must be half that. Double the volume, half the concentration. So I have 0.23 divided by 2, which will give me my initial concentration is 0.115. Right. So initially, these are the concentrations that they will have as a result of doubling the volume. Now, they said here, the change, if the concentration of CS2 changes, note that, changes by X mole per dm cube. So that means we're going to have X here. It changes by X mole per dm cube. But now, let's understand which reaction was favored. After the doubling of the volume, we saw that when we were explaining here 6.4, we saw that the reverse reaction was favored. So note, if reverse reaction is favored, remember this. We said, what do we do on the reactants? We are supposed to add on the reactant to find the number of moles at equilibrium, or the concentration at equilibrium. But what do we do on the product side? Because now if we favor the reverse reaction, the products are being used up, then we have to subtract from the product. Right. But then let's check here. How would we find our change for the sulfur gas? If we are saying this change by X, then what is the change in the sulfur gas? Now, that's where we look at the ratios. Remember, the change block relates to the ratio. So if the ratio is 2:1, and then the change here is X, that means the change in the sulfur, according to our ratios, needs to be 2X. Because we simply say X multiplied by 2, then divided by 1. That's 2X. Now, note, on the reactants, what must I do? I must now add, because the reverse reaction was favored. So that means the reactants are being formed. So that's 0.115 plus 2X. And then what happens on the product side? The products are being used up. So that's 0.25 minus X. Okay, and now to calculate Kc, we need to say Kc is concentration of the product over concentration of the reactant. And then remember, the ratio becomes an exponent. Now note that this expression does not change. Whether it's the forward reaction or the reverse reaction that is favored, Kc is always concentration of product over the concentration of the reactants. And then now, the concentrations that we are going to substitute are always these ones, the concentration at equilibrium. So we have our 0.25 minus X, and then over 0.115 plus 2X. Then remember, square. Now our Kc value still remains the 9.4 that was given in the question there. Why are we still using the 9.4 even though we are told that a new equilibrium has been established? It goes back to the fact that our Kc value can only be affected by a change in temperature. So having to increase the volume, decrease the volume, increase the concentration of any of the reactants of our product does not actually change the Kc value. So all those other factors can only shift the chemical equilibrium position, but then cannot affect the Kc value, right? So this is our expression. Remember, they said that we must not solve for X or we must not simplify. So that's how we're going to leave it. We have our final answer like that. 6.6 is saying the reaction rate time graph below represents further changes made to the equilibrium mixture. The volume of the container is kept constant. What do the parallel lines between TA and TB represent? Right. So if we see parallel lines like that, what are we supposed to say? What does it represent? We should always say, so whenever you see parallel lines there, it means that we are at chemical equilibrium. So we have reached a state of chemical equilibrium or dynamic equilibrium. So, or you can just tell them this is where the rate of the forward reaction equals the rate of the reverse reaction. Then, okay, 6.6.2, it's saying, what change was made to the equilibrium mixture at TB, right? Now, looking at what is happening here, we can see a spike up on the forward reaction here. Now, the spike up can represent that the concentration of one of these reactants might have been increased, right? But then looking at these two reactants, we can see that carbon here is a solid. And then remember, we said that the concentration of solids or liquid substances remains constant throughout the chemical reaction. So they do not increase, they do not decrease, meaning that the only concentration that could have been increased here is the concentration for the sulfur gas. So to indicate our change, we'll say there is an increase in concentration of the sulfur gas. Right, so that was the change that was made there. Now, 6.6.3 saying give a reason for the sudden change in the reaction rate at TC, right? So at TC, we can see both the forward and the reverse reaction decreasing there. And then we know that the reaction rate is aversive to a decrease in temperature. Remember, when we go back to our topic reaction rate or the extent of the rate of reaction, it says that if we increase the temperature, the rate of reaction increases. But if we decrease the temperature, the rate of reaction decreases. So which is why here when we are saying this is a decrease in temperature, we can even say with both the forward and the reverse reaction immediately decreasing, right? So we are sure that that is a decrease in temperature. So it's a decrease in temperature, right? So both the forward and the reverse reaction are decreasing there. Now they're saying fully explain. We want to know why are we so confident in saying there is a decrease in temperature? And there comes our explanation. 6.4.4, we are saying it's a decrease in temperature first, so that we know what we are explaining. So it's a decrease in temperature. Then point number one, we're going to point them to the fact that the rate of the forward reaction, the rate of the forward and reverse reaction decreases, right? So both the rate of the forward and the reverse reaction decreases. Now, but what we observe is that the forward reaction decreases more. So remember, all that we are explaining is what we can observe from the graph, right? The forward reaction decreases more. Now, note we are given here, the forward reaction is the bold line here, and then the broken lines are the reverse reaction. We can see the forward reaction dropping than the reverse reaction. And then which means, in this case, the reverse reaction is the one that is favored because it did not decrease as much. The reverse reaction is favored. We know a decrease in temperature favors the exothermic reaction. Favors the exothermic reaction. just like that we have explained. So please press the thumbs up button if you've enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit the subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.